Hello students. Okay, so last episode we zoomed all the way out and looked at the entire VLSI pipeline specification to silicon. Today we are going the opposite. We are zooming in like all the way in because here is a plot twist. Nobody tells you at the start of this course Verilog code is not one thing. It's not like Python where there is basically one way to write a for loop and you are done. Verilog can describe the exact same circuit in four completely different ways. And depending on which way you pick, your code is gone. Look, nothing alive. This is next episode, and by the end of it, you are gonna understand why your professor keeps saying level of abstraction like it's this deep physio- philosophical thing. It's not that deep, but it is the single most important mental model for this entire unit. Let's get into it. RTL design your Verilog code. Quick rewind. Last video we said RTL design stage 2 of the VLSI flow is where your Verilog code lives. Cool, true, no lies there. But here is the thing I glossed over on purpose. I said RTL code like it's a single format. It's not. Think about it this way. If I ask you to describe a circuit that adds two numbers, I could ask you to describe it four completely different ways. And all four answers would be 100% correct. One might sound like this circuit outputs the sum of A and B. Another might sound like a literal list of every single AND gate and OR gate and how they are wired together pin by pin. Both are the designs, both are RTL in the broad sense, but they read nothing alike. So today, whole mission, the four zoom levels of the exact same circuit, same hardware, same function, four totally different types of codes. The four levels. Here is the big picture before we go level by level. Picture it like this. You are looking at a circuit through a camera and you can zoom in or zoom out. Zoom all the way out, behavioral. You just describe what the circuit does, like reading a datasheet summary. No wires mentioned, no gates mentioned. Just this thing does X. One click in data flow. Now you are describing how the signals relate to each other using expressions. Think of this like writing an equation and Ohm's law style. Relationship between input and output. One more click in gate level. Now you are not writing equation anymore. You are literally placing individual logic gates and are not and wiring their pins together yourselves like you are populating an actual breadboard, all the way zoomed in switch level. This is the floor. This is individual transistor, the actual NMOS and PMOS switches that every single gate above this is built from. And here is a part that should blow your mind a little. All four of these describe the exact same physical hardware. Nothing about the circuit itself changes. What changes is how close you are standing to it when you describe it. That's literally what levels of abstraction means. It's not four different circuits, it's one circuit, four different distances. Let's start at the top, behavioral modeling. Here is the electronics analogy that's gonna make this click. Think about how you use an IC from a data sheet. Let's say you are using a 555 timer chip. You don't know, and honestly, you don't care what's happening to the internal transistor, the internal comparator, the internal flip-flop inside the chip. All you care about is the functional behavior written on the data sheet. If you configure it this way, you get a square wave output at this frequency. You are trusting the black box to do its job correctly, and you are only interacting with its documented behavior. That's exactly what Verilog behavior is. Look at this code on the screen. Always at the rate a comma b, if cell output equals to a, else output equals to b. Whenever A or B changes, if cell is true, out becomes A, otherwise out becomes B. That's a 2 to 1 multiplexer. But notice I never said the word gate. I never said wire. I never told the tool how to build this. I just described the behavior I want, and I am trusting the synthesize tool. Remember stage 4 in my previous video to figure out the actual gates for me. This is the highest level of trust you can put in the tool. It's fast to write, it's readable, but you have the least control over exactly what hardware gets generated. One level down, data flow modeling. And this is where I want you to think about Ohm's law for a second. V equals IR. That's not a set of instruction you execute step by step. It's not like first calculate I, then multiply by R, then wait, then output V. No, it's a continuous, always true relationship. The moment current changes, voltage changes with it instantly, continuously, forever, as long as the circuit is powered. That's precisely the mental model for data flow Verilog. Look at the code. A sign out equals to cell, question mark, A colon B. That assigned keyword is the whole personality of this level. You are not writing a behavior that runs when something happens. You are wiring a live continuous relationship between signals, just like P equals to IR is a live relationship between voltage, current, and resistance. The second cell changes out updates. No delay in logic, no step-by-step execution, just a standing electrical relationship expressed as an equation. This is one notch closer to the actual hardware than behavior because now you are thinking in terms of signal expression, but you are still not placing individual gates yet. Now we are getting real gate level modeling. Imagine you have got an actual breadboard in front of you, and instead of wiring an equation, you physically grab a 24740 chip. That is your quad and gate IC and 7432 chip. That is your OR gate IC. I hope you know the IC numbers. And you start running jumper wires from specific output pins to specific input pins. Pin number 3 of this chip connects to pin number 1 of that chip. No shortcuts, no equations doing the work for you. You are the one deciding exactly which gate connects to which gate. That's gate level Verilog. Look at the gate and A1 in the bracket N1 comma cell comma A, not N1 and cell comma cell, and A2 N2 comma N cell comma B, or O1 output comma N1 comma N2. Every single line here is literally placing one gate and naming its connection. A1 is AND gate instant. N1 is not gate instant. You are hand initiating each primitive. The same way you had hand place each IC on that breadboard. And wire its actual pins. This is the same 221 marks we just built with one line of behavior code and one line of data flow code, except now it takes four lines because you are doing the gate by gate wiring yourself instead of trusting a tool to do it. More control, more lines, way closer to the metal. And now the floor, the absolute lowest level you can go in Verilog switch level modeling. Remember that AND gate IC I mentioned, the 7408. What if you cracked open the actual silicon die inside that chip and looked at what's really happening electrically? You wouldn't see an AND gate anymore. You had see individual NMOS and PMOS transistors arranged in a pull-up and pull-down network, switching on and off based on voltage level at their gate terminals. That transistor level network is what an AND gate actually is, physically on silicon. Switch level modeling lets you describe hardware at exactly that resolution. Individual transistor, individual switches. It's rarely used directly in day by day to RTL design. Synthesis tools handle this layer for you, but it matters because every single gate you have ever used at every level above this is built from this. This is the true physical floor. There is nothing more fundamental underneath it. It's not code anymore at this point. It's literally the electrical switching behavior of silicon. Okay, here is why I have been hammering this so hard. Remember the syllabus, Unit 2, 3 and 4, gate level modeling, data flow modeling, behavioral modeling. Those aren't three random unrelated topics you have to survive back to back. Those are literally the same three levels. We just walk through, and in every single one of those units, we are going to build the exact same circuit, decoder, multiplexer, flip-flop counters using that unit's level of abstraction. So in unit 2, you will build a mux out of raw gate primitives, wiring it like a breadboard. In unit 3, you will build the same mux using one continuous assigned statement like an Ohm's law relationship. In Unit 4, you will build the same mux again using an always block describing pure behavior like reading of a data sheet. Same function, same truth table, three totally different looking pieces of code. And once you have built the same thing three ways, you are not just memorizing syntax anymore. You actually understand what each level is trading off. Control versus convenience, low level, precision versus high level speed. So here is your one sentence takeaway from this whole video. 4 altitude, 1 circuit. Behavioral, data flow, gate level, switch level. Same hardware, 4 different distances from the metal. Every unit coming up in this playlist is just you practicing one of those altitude. Next video, we are tackling something I have mentioned like three times already without full explaining it, concurrency. The idea that hardware doesn't execute line by line like a normal program. It runs all at once. We are gonna crack open exactly what that means inside actual Verilog code. And trust me, this is the concept that either makes Verilog click for you or makes it feel confusing forever. You want to be in that first group. Subscribe, stay in the playlist, and I will see you in the next video. Dear students, we are following the syllabus of ED302 Introduction to HDL according to RGPV syllabus. Do watch the playlist, and if you enjoy, like, give thumbs up, share this video with your friends and subscribe the channel. Your subscribe means lot for me. Thanks for watching.